I hope my talk also has to do with, well, at least probability and field theories, so the general topic of the program. Also, maybe more specifically, there are some aspects of integrability and conformal bootstrap, so maybe even topics of the workshop. I'll stay at a fairly at the level of an overview for most of the talk. I do try to make at least the statements precise. I will not give details of proofs, but my plan is to describe the ingredients of the proofs and maybe do it in such a way that at least the flavor of the technicalities is also yeah, thanks a lot for the organizers of the really exciting looking program and workshop, and thanks for the invitation. So I'll be describing some joint work with various people, so some older work with Clément Honger and Fredrik Wiklund, some slightly newer work with Adam Carrillo and Lara Beksad, and some work in progress with Dima Chelkak and Kostya Isro. So in local fields of lattice models and conformal field theories. So in terms of overview, what this is about. Here are the objects we're interested in. So you see some random configurations in probabilistic models living on discretized space. So underneath there's a regular grid of some sort in each of these models. So in the middle picture there's a hexagonal grid, in the other two there's a square grid of small mesh size, and this mesh size is thought of as a microscopic length scale in these models. And the idea is that the definitions of the probabilistic models involves only interactions in the microscopic scale, so in the scale of the lattice mesh, but that leads to interesting physics in the macroscopic scale. So, right. And how do we capture even the difference between the microscopic and the macroscopic scale? We'll treat this lattice mesh size delta as a parameter of the models, and we'll try to form scaling limits, i.e. we try to take that microscopic length scale to 0. And whatever remains in such a limit is basically by definition macroscopic. Yeah, maybe a point about the perspective, maybe the illustrations suggest more random geometry perspective, but I'll be taking the original point of view of physicists of focusing on correlation functions in this talk. So indeed, we shouldn't disregard physics insight in this area from 20th century research in statistical physics. There are some insights I want to highlight, in particular two. The first one is that these probabilistic models near critical statistical physics, they are described, if you believe the physicists, by quantum field theories in Euclidean space. Euclidean space as opposed to space-time with a Minkowski signature. So I think it's a remarkable thing that these probabilistic models, statistical physics, is described in the same language as particle physics, but since this is a program on probability and field theories, maybe to this audience is not a surprise. So it became such commonplace a statement in the last century that the first sentence of Belavin, Polyakov and Chamologikov paper was that we studied the massless quantum field theories describing the critical points in two-dimensional statistical systems. Statistical systems described by quantum field theories, no big deal. Okay, so that's a part of the insight that we take from physics. And the more specific one is that if you're exactly at criticality, and especially in two dimensions, these scaling limits, these quantum field theories that describe the scaling limits of these probabilistic models are not just any old quantum field theories, they're going to have conformal symmetry, conformal invariance. So there's something called conformal field theories, and the main algebraic structure that they have by virtue of these conformal symmetries, two commuting copies of Virasoro algebra acting on their spaces of local fields. Right, so this is exactly what leads to some of the topics of this workshop. So integrability, conformal bootstrap, etc. And at least if you have something like degenerate representations, then you do get some form of exact solvability of these models. And they led to a lot of exact and correct predictions in the physics literature. Exact and correct doesn't mean the same thing as rigorous. So for mathematicians, these have been a little bit of a challenge, but there's been progress in rigorous conformal invariance statements by, for instance, Kenyon, Smirnov, Chelkak, Homer, Isirov, and others. Mainly with tools of discrete complex analysis. Okay. Lots of specific results about conformal invariance, but I would argue nothing like what Belavin, Polyakov, and Chamlogikov said here in this pioneering paper, that the local fields form operator algebra that can be classified according to irreducible representations of the Virasoro algebra. That does not appear in the math literature that I'm quoting here. Okay, so how would we start making sense of these mathematically? I think we first admit that the main object is local fields of the quantum field theories. So how do we connect these to the probabilistic models? First of all, there's one reason to focus on local fields of a conformal field theory is that there's a principle called state field correspondence, which says that the space of local fields is exactly the state space of your quantum field theory. So that gives another justification that this is a fundamental piece of data in a conformal field theory. I'll take the point of view of viewing them as local fields nevertheless, because the observable quantities in quantum field theories are correlation functions, and correlation functions of what? Of local fields. So you have some local fields f1 up to fn located at some points z1 up to zn in a physical domain, and you form a correlation function of them. Now, for the purposes of this talk, I'll take the point of view that we know already, or it's given what local fields in a CFT are. This, leads to some interesting philosophical questions and interesting mathematics of making precise sense of that. But at least for concrete field theories that we'll look at, we can describe the spaces of local fields very concretely. So this part I'll consider as given. And the more interesting part is how does it correspond to something in the discrete, something in the probabilistic world. And since the observable quantities in probabilistic models are typically expected values of products of random variables, if these random variables are well localized, they are a good candidate for the notion of local fields in the probabilistic models. All right, and since almost by the axioms of conformal field theory, on the space of local fields of a conformal field theory, you have these two commuting actions of Virasoro algebra. Wouldn't it be great if we had exactly the same structure on these spaces of local fields of lattice models, so somehow built out of random variables? This might seem somewhat crazy because the Virasoro algebra was supposed to describe and supposed to be the result of conformal invariance of your field theory. The lattice even doesn't have any conformal invariance in it. So this might seem overly optimistic, but due to discrete holomorphicity and integrability, this can actually be realized once you set up things correctly, and I'll come back to that later. So let's dream that we have at least the same algebraic structure on the space of local fields of a lattice model as we do on the fields of conformal field theory. So then, what would I envision as a correspondence between the two? Well, the most naive would be that to every locally defined random variable, I could associate a field of a conformal field theory, and correspondingly to every field of a conformal field theory, I would have a corresponding random variable in the lattice model. So that would be the most naive way of thinking about it, and I'm going to be exactly that naive. So I want the one-to-one correspondence which respects this algebraic structure, so it's an isomorphism of Virasoro modules. So that's how naive I'm going to be. And now the remaining thing is I haven't yet related the observable quantities, the expected values of products of random variables, to the correlation functions in the continuum. And for that, one has to take a scaling limit. So one needs to take the lattice mesh to 0. These don't converge on the nose, so it's not. You need to do something. You need to renormalize the lattice local fields with the random variables. And fortunately, since scaling transformations are a special case of conformal transformations, the algebraic structure that represents the conformal invariance contains the information about the scaling dimensions. It contains the information about by which power of the lattice mesh do you need to renormalize your random variables. Somehow that part of data is included in the algebraic information, if our first two dreams were realized. So, yeah. I think you've seen statements of this form in the literature, that if you renormalize some random variables correctly, then the expected values of them converge to conformal invariant quantities. Now, the difference to most of the statements in the literature is that I want this for all of the local fields in the theory, which is an infinite dimensional space carrying these Virasoro representations. So I want this really in the sense of Belavin polygon and homological abstracts. Right. Okay, so these are my dreams. What is the current status of these dreams? The first audacious dream of having the Virasoro representation on local fields of lattice models has been realized in 3 different probabilistic lattice models. For the discrete Gaussian Free Field and the Ising model, this was done in an older work with Hongler and Wiklund. And for a model that is a discretization of symplectic fermions built out of double dimer random configurations, this was done by David Adamecarrillo. Okay. The other 2 dreams have been written up for the simplest of these models, so the discrete Gaussian Free Field, in a joint work with Behzad and David. There is progress in the other cases, and maybe if I have time, I'll say something about that as well. So this is the current status. Of course, there's an interesting question. Are there other models besides these 3 for which one could hope to realize the dreams? That I have nothing to say at the moment, but I think it would be exciting. Okay, in order to give precise statements, I'll have to, unfortunately, give some precise definitions, so I'll try to be brief. I'll define 2 probabilistic models, partly so that I'm able to compare which parts of the precise statements do depend on the models and which parts of them are sort of, to which extent are is the philosophy similar. So I'll define the Ising model and discrete Gaussian Free Field. So let's take a finite piece of the square grid as our discretized domain. So this is the square grid of mesh size delta. And later on, you should think that this actually approximates a continuum domain, so an open-bounded subset of the plane. But for the moment, any finite piece of the square grid is fine. I should also fix boundary conditions. Maybe I won't say too much about that. Okay, then the Ising model is a random configuration of spins on the vertices of this finite piece of the square grid. So in order to define the model, I should give the probabilities of configurations of spins. I will describe those probabilities at the critical inverse temperature beta, because at criticality we expect conformally invariant scaling limits. So a configuration of plus minus 1 spins on the vertices has probability proportional to exponential minus this inverse temperature parameter times the energy of the configuration. And the energy of the configuration has a contribution from every nearest neighbor pair of vertices, so pair of vertices at exactly one lattice unit from each other, which is the product of those spins with a minus sign. So the energy is it's energetically favorable to align with your neighbors, for the spins to align with your neighbors. Okay. And the strength of this preference of alignment is tuned by the inverse temperature parameter, which we always take to be critical. Now, this would be the correct definition of the Ising model with free boundary conditions. If you want some other boundary conditions, you'd include extra terms in the energy. So that's the definition of the Ising model. For comparison, I'll also take the other model, a discrete Gaussian free field, which is a kind of a random height configuration. So for every vertex of the discrete domain, there is a real valued height parameter. And now, instead of giving probabilities of configurations, I'll give a probability density, which is exponential of a quadratic expression on the heights. So a Gaussian here, and the quadratic form here is the discrete version of the Dirichlet energy. So there's a contribution again from every nearest neighbor pair of vertices of the square difference of the heights. Okay, so that defines the model by a Gaussian density. This would be literally okay if I took Dirichlet boundary conditions and then I included some boundary terms. I will want to take Neumann boundary conditions as well, but I won't write down the precise definition. Those who know will know how to make sense of Neumann boundary conditions. I won't bother writing that down unless you specifically ask. Okay, so these are two models. So the important thing is that the first model has plus minus 1 degrees of freedom on vertices. The second one has real degrees of freedom on vertices. So how do we make sense of local fields? Let's start from examples. So localized random variables. Let's say take the Ising model. If we're on our discrete domain at any point z, then suddenly the spin at z, this plus minus 1 valued random variable, should be a locally defined random variable at the point z. Now, for every different point z, this is a different random variable, but I do want to think that it comes from one sort of notion of a spin field. So all of the different random variables indexed by the different points in the domain, or even if we take a different domain, different boundary conditions, we have a different probability space, and whatever point there, I have still the spin random variable in that model. I want to think that they arise all from one notion of an abstract spin field that then evaluates to a random variable in any discrete domain at any point in the discrete domain. Okay, you could have, of course, more complicated example. So, for instance, this contribution to the energy from a vertical edge from a point to its nearest neighbor to the north. That contribution to the energy is fine, and for instance, in the work of Smirnov and Hongler, if you subtract from it a suitable infinite volume constant, this is an energy field which has interesting scaling limits. So this would be another example of a random variable. Here's another example in the Gaussian free field case. So this is kind of a gradient squared of the discrete Gaussian free field. So things that depend on finitely many neighbors of the point of insertion are meant to be local fields. Basically, the local field encodes a rule of a translation invariant rule of building a random variable out of the degrees of freedom in a finite lattice neighborhood of the point of insertion. So to make this precise, now we have to do something model dependent. So for the Ising model, I could take as the space of field polynomials the formal linear span of finite subsets of the infinite unit mesh square grid. And then the way to assign let's say, a finite subset of the unit mesh square grid a random variable in a domain omega delta inserted at z would be to view the z as the origin of your lattice and then translate the points of the finite subset by that many lattice units and then form, let's say, the product of those spins. And then, of course, extend by linearity to the formal linear span of these. Okay, so that's an Ising-specific definition of field polynomials. How about the discrete Gaussian free field? Well, you could, I'll actually do the gradient of the discrete Gaussian free field, so I'll only allow to consider differences of field values, which then make sense with either the Dirichlet or Neumann boundary conditions. And then we could take as the space of field polynomials, again, something indexed by the unit mesh infinite square grid. So there would be the polynomial algebra with those indeterminates, and then the indeterminate at point u gets mapped to the difference of the field values from the point of insertion to a point of insertion translated by that many lattice units. I don't know if I described this the most concretely, but I wanted to emphasize that the precise definition of field polynomials does depend on the model, but the philosophy doesn't. All right. So this is almost the definition of locally defined, well, this is the definition of locally defined random variables. In order to set things appropriately so that we might have this Virasoro action, we need to do something essential still. There's an observation that could be that two different field polynomials give rise to exactly the same correlations as long as you don't really insert the products of random variables at microscopic distances from each other. So this would be physically indistinguishable in observable quantities, and we should sort of identify such objects. So the definition of null fields, another way of saying that the two things are indistinguishable if their difference has zero correlations in all physically meaningful correlations. So that would be called null. So a field polynomial would be called null if there exists some finite number r such that whenever your point of insertion, so for whatever discrete domain, for whatever point of insertion such that you have at least r lattice units to the boundary of the domain, and for whatever other points, as long as those other points are at least r lattice units away from your point of insertion, then when you evaluate that abstract field polynomial to a random variable and you take its products with these other things, the expected value is zero. Literally zero on the nose and not approximately zero.
Zero, or the limit as delta goes to zero becomes.
Yeah, it's a good question. So I want this to be literally zero. So I want that there exists a finite amount of lattice units such that anything that is evaluated, any correlation function that is only probing, all of the other insertions are at least, at least these r lattice units from my insertion. I want this expected value to be literally zero. So that's a very good question.
Should I think of that as being a special feature of this model, or I mean the fact that you could put it to be actually zero? I mean, in some other models, maybe you need to put an exponential decay in R, or?
I think if one wants the dreams of these making sense of these local fields and really having this isomorphism of local fields as Virasoro representations to the CFT fields, I think one would want this to be literally zero on the nose. The point is that I wanted to really identify my space of lattice model local fields with the CFT local fields sort of as abstract objects before even passing to the scaling limit. So I think for that reason, at least if you follow exactly the formulation of the dreams as I had, I would expect that one always needs to quotient out by such things. Yeah, so right, so this is what I would, field polynomials which would have this property that they have zero physical correlation functions, I would want to identify with the zero field, which is, I just take the quotient of my field polynomials with the null field.
So are there no polynomials which satisfy it in the limit, but not exactly? So that was a badly phrased question. Are there any that?
Okay, that's another good question. So the thing here is also that I'm taking this in every finite lattice model, lattice domain separately. So you'd even have to specify, if you want to phrase this in the limit, you'd even have to specify how do you approximate domains where you put other things. And since there was the notion of, I mean, if you don't renormalize in that case, so you'd also have to decide about renormalization. So for this question to have a precise answer, I'd have to specify a number of things. So I don't think I can give a precise answer to that, but I will really take the point of view that I wanted to quotient out by those fields which literally on every finite lattice domain, and as soon as you went a finite number of lattice steps away, gave zero correlations. And those are the ones that I want to quotient out of these abstract field polynomials.
Do you have a simple example of low-grade polynomial? That is?
Yes, so that's a very fair question. Let me maybe just before that say that one can, so this was specifically for the Ising, so I asked that if I test against spins elsewhere, I got 0. You can give exactly the same sort of definition for the discrete Gaussian Free Field, and giving an example of that is maybe slightly easier for the discrete Gaussian Free Field. So if this answers the question, then so phi was the field, and now if I take phi at z plus I delta plus phi at z minus I delta plus phi at z plus delta plus phi at z minus delta minus 4 times phi at z, so this is kind of a discrete Laplacian of phi at z. This one will have 0 correlations basically by the domain Markov property of the free field, as long as depending on only these 5 points on the lattice, and as long as anything else that you insert doesn't touch these 5 points, then the correlation function of that object will be literally 0 on the nose. So this is an example of an output. In the Ising model, you can give an example as well, a fairly simple example, but maybe this gives the idea already. All right. No, so that's important because in order to have this audacious dream of having Virasoro action on spaces of local fields, we really did need to quotient out by this relation. But now we've defined the space space of sort of, we've set up things correctly about the local fields. So we defined locally defined random variables by this abstract notion of local fields, and we only quotient out by this relation, which admittedly is a very implicit relation. It's requiring something in all domains, it's requiring the existence of a finite number of lattice units, etc. But at least it was a well-defined quotient. Okay. So now we can then state precisely the first result, which answers the first dream in, well, let me state it for the discrete Gaussian free field. So, and then state it for the others a little more briefly. So there are really two families of operators indexed by integers, Ln and Ln bar, n being the integer, on this space of local field polynomials quotient by null field polynomials, which satisfy the commutation relations of Virasoro algebra with the central charge C equals 1. Okay. Two commuting representations of the Virasoro algebra exactly as one should in the CFT. This is for the lattice model local fields. Stating the result also for the Ising model is very simple. You just change, of course, the space of local fields, you change to Ising local fields, and the central charge you change to 1/2. And David Carrillo has a result about discrete symplectic fermions, and the central charge will be -2. So at least the statement should make sense. I'll later describe some ingredients in the proofs, but I hope I've given a precise statement of how the first dream is realized in two of the models, at least.
Okay. Sorry, does it have a structure of highest weight representation as weight 0 or for this representation?
So this that's exactly actually the content of the second. So this one only says that the space of local fields is equipped with the Virasoro representation. It doesn't say what is the structure of that representation. So it's exactly the content of the second statement that addresses the structure of that representation. So this is the existence of a representation. The next one is there's an isomorphism to something we know. Okay. So, for instance, for the gradient of the discrete Gaussian free field, this space of local fields, which I remind is field polynomials modulo null fields, is isomorphic as a representation of two commuting Virasoro representations to exactly what it should be in the very concrete conformal feature of a free boson. And what that is, it's a tensor product of two Fock spaces in two different chiralities. So the two copies of the Virasoro algebra in particular act on the two copies separately. So so the point is that this is a completely explicit representation, and in that sense, it, for instance, tells that this representation contains a highest weight representation of highest weight 0. It also contains a highest weight representation. Well, actually, since there are two chiralities, highest weight 0, 0, so 0 in both chiralities. There's also other highest weight sub-representations there, if you view it as Virasoro representation. But this exactly answers what content is there in the representation. And now, so let me just describe concretely what this Fock space is. So I'll apologies for the probabilistic audience. I'll do an algebraic description of this because it's actually the one that is more convenient to work with when we prove the results. So one way of describing what the Fock space is algebraically is to start from an associative algebra with generators JL for L an integer and commutation relations of this form. So I take an associative algebra of this kind. I call this the Heisenberg associative algebra. You should think of it as a chiral symmetry algebra of the free boson, although maybe the more principled approach of that we'll hear in E.J. Huang's talk later this week. So maybe you want to extend it to a vertex operator algebra. think of it as the chiral symmetry algebra of the free boson. Now, the Fock space is then algebraically constructed by viewing the algebra as a left module over itself and taking the ideal generated by the positive index generators and quotienting that out. So that's still a representation of the Heisenberg algebra. You could give an explicit basis for it, so this is something we understand extremely concretely. Okay, so this is now a representation of the Heisenberg algebra, but it also becomes a representation of the Virasoro algebra by Sugawara construction. So these formally infinite sums act locally finitely. So on any vector, if I act by this sum only finitely many times are non-zero, and you can verify by algebraic manipulation that they satisfy Virasoro commutation relations with central charge 1. So this equips it with the structure of a Virasoro algebra, and now we know exactly the object on the right-hand side, which is exactly the free boson state space. And the second statement is isomorphism of our space of local fields of the lattice model to that local fields space.
Yeah. So if it's weight 0, then you should have a null vector at level 1, right? But this one is already at level 2 now?
Yes, I know that this doesn't even appear here because it was quotient out before.
Maybe I'm mistaken, it looks like this is L-2, but where is it L-1?
This is not L-2. L-2, if you take the holomorphic L-2 and not the anti-holomorphic L-2, that should give you the stress tensor. This is not the stress tensor, it's something that is null.
And it's probably L-1 actually.
Yeah, this is. Yeah, it's probably L-1, L-1 bar.
Sorry. Maybe once you show me the J.
It's not there because it's not there on the left-hand side. We quotient out that before we did anything. It's just not there. I can't give a formula for it because it doesn't exist.
-1 of the vacuum is 0 anyway, so you don't see it.
Yes. Yeah, I mean, I can't tell what this is because this is not in the space. I quotient it out. It's 0. this is 0. Yeah.
So it's also statement that you can have assessment at the level of the Heisenberg algebra directly.
Sorry? Yes, it's an isomorphism at the level of Heisenberg algebra directly. Yes. And that's actually the way we prove this. I wanted to focus on the Virasoro algebra because, for instance, in the Ising case, if you really want to random variables, there would be a kind of a Clifford. So morally, there is a Clifford algebra representation, but it's not quite there because odd numbers of fermions don't actually act on random variables. So what you can state there for the Ising case, in principle, is only about the Virasoro algebra. So that's why I stated this only for the Virasoro algebra. You're quite right that it holds for the isomorphism of the Heisenberg algebra, and that's actually also the way we prove it.
So maybe this is related to what you just said. So proving this theorem 2 means to show this identity, so to construct these JLs and then prove that the LNs are given by this, or so why doesn't theorem 2 implies theorem 1?
The whole thing is we need to. Theorem 1 said that this space had. Theorem 1 said that this space had the action of Virasoro algebra, which indeed involves constructing actually something like JLs and this LN. And then this is to prove that now, okay, it has a representation, but the structure of that representation is exactly on the nose, the tensor product of Fock spaces. This is describing what is the structure of the representation. Theorem 1 says that there exists a representation.
So concretely, what do you need to prove additionally after you know after you exhibit lattice operators.
So I was actually planning to come to the outline of the proofs later, but should I try to comment on it at this stage? Maybe?
No, okay, now if you come to it later.
Actually, how much do I...
20 minutes left.
So maybe I'll return to that later. But roughly speaking, the first statement says that the lattice model local fields have a Virasoro representation. The second statement describes exactly what is the structure of that Virasoro representation. So it gives an isomorphism to a known representation, which is exactly the one you expect from a CFT. Yeah.
So when you wrote the thing on the right, F tensor F bar, and you said that's exactly what it expects from theory. I tend to disagree. What I would have expected is the direct sum indexed by the irreducible representations of the Heisenberg algebra of such tensor products. So are you saying that these other guys are just not realizable as lattice local polynomials?
Okay, that's a fair statement. So the thing is that we took as the model the gradient of the discrete Gaussian free field. Now, one thing that I didn't allow for this is, for instance, exponentials. Okay, so first of all, I only allowed polynomials in differences of the field values in my discrete model. I would argue that I can build also a free boson theory which also only has these as gradient of the polynomials in the gradient of the free field as its local fields. Now you're quite right that that's not the standard thing to do. Often one would also include exponentials of the free field, so vertex operator is sometimes called. Different notion of vertex operators than we will hear in a talk later. I get this question basically every time I give the talk. So there is a, one can extend this to include also exponentials. So I then have to go back and modify my space of local fields for the model. So I should now not just take polynomials in the gradient, but I should allow for also exponentials of the field value. Then it would no longer make sense with the Neumann boundary conditions, so I'd have to give up something. So I'd have to go back and modify something, but that can be done. There are some things. Yeah, maybe we can discuss later. But that
you're aware of all that, yeah. So,
yes. Yeah. So the reason I got exactly the chargeless Fock space is because I looked at polynomials in the gradient. Okay. So yeah.
Simply, it's a stupid question maybe, but when you have a Heisenberg representation, there is a Virasoro Sugawara construction for every possible central charge. What makes you stuck at one?
Yeah, that's a completely fair question. Okay, so maybe this will become, I can state something about that after stating the scaling limit result, because on an algebraic level, yes, you can have representations at every central charge. Then the question is, once we relate these to correlation functions in conformal field theory, do we have that the Virasoro action accurately reflects conformal transformations? And that will only happen for a particular case. I don't have a specific clear theorem about that, but that's a fact. But it can only be stated once I've described the scaling limit result, which is theorem 3. So maybe I'll get to that, and then answering your question makes more sense. So we'd like to have some expected values converging to conformal field theory correlation functions. For the moment, I'm not gonna, so I owe you, of course, a definition of conformal field theory correlation functions for the free boson. Let me just say quickly that it has these correlation functions on the right-hand side have a construction from the Gaussian free field and a bootstrap procedure. let's not focus on the right-hand side, let's focus on the left-hand side. So what do we put inside these expected values? Well, let's fix some n local fields, which now by the isomorphism of theorem 2, I can think of either as living in this tensor product of Fock spaces or really as field polynomials modulo null fields in the lattice model. The isomorphism allows me to think of them in two different ways. And without loss of generality, I can break my fields into since I know the isomorphism and since I can explicitly verify that L0 and L0 bar are diagonalizable on the Fock spaces, they're then also diagonalizable here, and I can break my fields to finite linear combinations of eigenvectors of L0 and L0 bar and describe scaling limit results separately for all eigenvectors. So I'll do that, I'll assume my field is broken to a linear combination of eigenvectors, so I look at an individual piece. Now, for the scaling limit result, I need that my discrete domains approximate a continuum domain. So let's assume in Cartesian sense that the square grid domains tend to an open-bounded, simply connected subset of the plane. And let's also assume that the points where I insert approximate some points in the continuum domain. Let's take, for instance, the closest lattice points to the given continuum points. And then if you put inside the expected value the evaluation of your abstract field, and it doesn't depend which representative you put because the expected value will differ by only 0 if you choose a different representative. So you put any representative of your local field, evaluation of it as a random variable here, and you renormalize by lattice mesh to the power of these L0, L0 bar eigenvalues, then you have convergence. It's the convergence statement. And I should say, it's a separate statement whether you take Dirichlet boundary conditions or Neumann boundary conditions. So the probabilistic model is different, although the rule to build the random variables was the same. Same random variables in or same lattice local fields in two different probabilistic models, Dirichlet and Neumann free field. Expected values are with respect to a different probability measure, and the CFT correlation functions will be different, but in both cases they have a construction from Gaussian Free Field and Bootstrap. Yeah.
Do you think we'll be able to put some periodic boundary conditions or get like this convective
The convectified GFF is definitely possible. I would say that okay, if you're in the simply connected case, I think Dirichlet boundary conditions. Okay, you're maybe thinking of having multiple boundary components, and you could have a different sort of a value. Yes, I think that can be done. Yeah, I think that can be done. Yeah, let me maybe make the statements in the simplest cases. And for instance, the Neumann case would be, exponential would still not make sense because there would be the additive constant ambiguity. So, yeah. So let me speak to only Dirichlet and Neumann boundary conditions for the simplest case. All right, but at least we have what the convergence result of renormalized random variable for evaluation of abstract local fields. We have their convergence to something, and of course I should describe what this something is. And this is where some of the themes of the workshop come in. So this is sort of a bootstrap construction. Just quickly, these three properties uniquely determine.
Could I ask you to quickly say how you implement the notion of Dirichlet and Neumann boundary conditions on the lattice, because you're using it, but you haven't said how you actually do it as well.
Yeah. So the Dirichlet is fairly simple. I take this quadratic action and I just require the values to be 0 on the boundary. Neumann, maybe my preferred definition of it is to define a Gaussian process indexed by zero average test functions. Exactly analogous to what is in, for instance, Nathaniel's and Ellen's book on the continuum GFF. Yeah, I do discrete zero average test functions, and I only allow the field to be mollified with zero averaged functions, and then I give the covariance structure of that. Maybe I can describe this more concretely afterwards. Yeah, okay, so the right-hand side involves CFT correlation functions, and they're uniquely determined by three properties: bosonicity, so symmetry under permutation of which order you put your fields in there. Then somehow the starting point of the construction is to describe correlation functions of currents, and they would be exactly the integral kernel of these multi-point derivatives of the free field, where the free field would be either the Dirichlet or Neumann continuum free field. And then the last piece, which is the bootstrap piece, are here written as an OPE of a current with one of the fields. Maybe since I'm running low on time, I will not elaborate on that, but there's kind of a, yeah, conditions which uniquely characterize these, and we can prove that the convergence happens to something that satisfies those properties. Okay. All right, so then I actually, how much time do I have for the ideas of the proofs?
7 minutes?
7 minutes, okay. Yeah, so I'll try to say something about what goes into each of these three pieces. So, right. So first of all, equipping the space of local fields with the Virasoro representation has, let's say, maybe 5 main steps, and maybe the interesting one to focus, notice at the very beginning, is that instead of constructing Virasoro generators directly, we construct first kind of Heisenberg generators acting on that, and then do a Sugawara construction. So we want to reduce this problem to something simpler, Heisenberg currents, and the advantage is that for Heisenberg currents we get to use discrete holomorphicity ideas. So that's the main advantage of doing that. Okay, so we describe discrete currents, which are sort of discretized finite difference operators that mimic the D and D bar in the continuum. Okay, so I'm not gonna write down the precise discretization, but this sort of gives a flavor. Finite difference operators discretize currents of the free field. Then you'd have a notion of discrete complex contour integration with good properties. So many properties that you'd expect from continuum complex analysis. Maybe the thing to note is that this is a notion of bilinear integration of products of two functions defined on two different lattices. So one function is defined at the midpoints of the edges, the other function is defined on kind of a dual lattice to that. Okay, why did we want the bilinear notion of integration with good properties? So the thing is that we then take these currents and weight them with some weight functions, which we take to be kind of monomial functions. So these are just the weight functions, and then we can integrate the current times a weight function to define the Heisenberg generators. So this is very analogous to what one would do in the continuum. Maybe the thing to note is that in the discrete we needed a bilinear notion of integration where two functions, the weight function and the current, lived on different lattices. But the discretization of complex analysis is good enough, there's residual calculus, etc., so you get a lot of properties that you expect also in the discrete. Then you prove Heisenberg commutation relations for the current modes using exactly these discrete complex analysis and residue calculus, and it looks exactly the proof in the continuum. So you act by two modes in one way or the other. So either you act first by one and then by another, or first by another and then by one. And then you deform contours to satellite contour and you do some residue calculation and you get the desired commutation result. And the last step is indeed Sugawara construction. That's pure algebra, so that can be done in your favorite proof assistant if you wish. And if you don't know what is your favorite proof assistant, you've come to the right place. Bonn has a professor of formalized mathematics, so you should maybe go and ask Floris van Doorn about what should be your favorite proof assistant. Okay. Anyway, so so the last part is algebra. Okay, so then maybe very quickly about theorem 2. So maybe this pertains to what needs to be verified. So first we recall that the left-hand side here is the quotient of field polynomials modulo null, and the right-hand side we've constructed as this quotient of the associative algebra by a certain left ideal. Okay. So now we make one very simple observation. If we take the constant field polynomial 1, then a simple calculation that of course requires giving the definition of these Heisenberg modes, which I haven't done, but the simple calculation shows that the equivalence class of the constant polynomial is annihilated by the positive Heisenberg generators. And now, by construction, the Fock spaces had the universal property that you have a morphism of Heisenberg algebra representations out of them whenever you find a vector in another Heisenberg representation with this property. So for free, you get a mapping from these Fock spaces to your field polynomials. And moreover, since the Fock space is actually irreducible, this mapping is either zero or an isomorphism, zero or an isomorphism to a subrepresentation, so zero or injective. And it's not zero because the field polynomial 1 is not zero. So this is actually an inclusion of the right-hand side to the left-hand side. So it's straightforward, almost automatic that we have the right-hand side contained on the left-hand side. So the whole difficulty is in proving the other direction. How do we prove that the left-hand side is not bigger than the right-hand side? And the idea is to first, the basic idea is to do dimension comparisons. First, we restrict to linear local fields, which unfortunately are still infinite dimensional, but we then further do a filtration by the radius of the support of the linear local field, and then we get finite dimensional subspaces, and then we can prove that filtered dimensions on the left-hand side are not larger than filtered dimensions on the right-hand side. So in the space of linear local fields, there's nothing extra on the left-hand side compared to the right-hand side. Okay, and then to get from linear local fields to arbitrary local field polynomials, there's a notion of normal ordered products, and you verify that normal ordered products pass from field polynomials to the quotient by null fields, and you check subjectivity, and you have the characterization of linear factors, and then you conclude. Okay, so then you get that there's really nothing extra on the left-hand side compared to what is on the right-hand side. I think I'm sort of out of time. The last statement about scaling limits is, roughly speaking, reduces to checking Riemann sum approximations to integrals, converge to integrals. So maybe I'll leave it at that. There's work in progress in the remaining parts, but I think I should stop here. So thank you very much.